Hello everyone, and welcome to another Jura video, where we're making a programming language in Java, because it's fun. And last episode we actually made Jura quite a bit more powerful by adding the ability to make custom functions. So this is what this is the file we did last time. So we can have parameters, return types, return statements, void returns, all sorts of things. And I noticed at the end of the last episode, after I finished recording, that we've left the ability to have recursive functions, but we never actually tested it. So I wrote this recursive, naive implementation of the Fibonacci number generator. Naive because it will doesn't have any like memoization. You know, the higher the number you call into here, the exponentially slower it's going to get. So I've only limited it to the first 10 Fibonacci numbers, but what it does is that it checks for the base case, 1 or less, it returns the input. Otherwise, it will sum the last two Fibonacci numbers recursively. And I've just got a little loop that counts up to 10. So if we run that, we can see we get the first 10 Fibonacci numbers, no problem. If I increase it to, say, like 20 and try again, it was still pretty fast. What about 30? Still kind of fast. Okay. Oh, there we go. Okay, so once we get to 40, you can start to see the slowdown. But that's not too bad. You know, for a language that I've just like cobbled together, it's kind of fast. And that's just because it compiles to Java bytecode, so the JVM is doing like all the heavy lifting for me. Which is fantastic, because then I don't have to worry about it. So today, something else we did actually yesterday in the last episode was we kind of improved the type checking, or like the type parsing, like the actually figuring out what type we mean when we say, you know, int, and we kind of left it open to have more types in the future, and in fact that's all the way in the parser. So somewhere last time, this is all a bit of a mess. Here we go. We added this function to parse a type expression, but we only ever return a basic type expression, which is just one of these where it's a single token. What I think we want to do today is have arrays. I'll just call it array.jura. And arrays are just going to look like regular old Java arrays for now. We'll see if we need to get fancier with it in future. But what I'm thinking is we're going to let's do it with the initializer. So what we can do is just the Java syntax like this with the curly braces. But as I said at the end of the last episode, I really like the idea of having structs in Jura, or at the very least having like this kind of initializer syntax for something typey. So I think it makes way more sense if the array literal syntax uses square braces, because that's what you use for the array type. Why do you use a different kind of bracket when you initialize it? I don't know. So that is what we're going to compile, and then, you know, we want to then be able to index an array, and we want to be able to assign back to an array. Sure, 12, why not? And then make sure that it actually updated. So this is what we're going to try to compile today, at least for the first bit. I think we might be able to finish this relatively quickly, and then if we do that quickly enough, maybe we can move on to something else. But we'll see how long it takes. If this does end up taking a while, then that'll be all the episode is just arrays. So let's do it. Let's bloody do it. So we'll start with the simplest case, which is this. Variables in Jura currently have to have an initializer. So I am going to basically do this rather than, you know, something like this, which I think would be really easy. But I don't want to deal with uninitialized variables yet. That's going to require some more sophisticated tracking in the compiler, which I don't fancy writing. So let's stop yapping and let's do this. So we, as far as I know, do not have these brackets in Jura yet, so we might have to go and add them. Let's see. Yeah, we have parentheses and curlies. So let's have an open square and a closed square. Then we need to lex them. So case open single char token kind open square, and then the same thing for this close square. Boom, there we go. Now we just need to parse this. So this is going to involve adding a lot more constructs to the language. So let's go to the parser. So rather than just immediately expecting an identifier, we should peek. We should say if peek, or better yet, switch on the peek and say default will report a diagnostic unexpected token. Is that right? Ooh, that just returns us the kind, not the token. Let's leave the default as this. The default is just going to be... Wow, that's not how you do that. Default is just going to be a basic one. Because then this will handle that error handling for us to say, oh, we expected an identifier at least, and we didn't get one. So we have a new case, which is an open square. So first of all, we need to... oh, hang on. No. That would be what we're parsing. And I've talked about this before, is like some languages, I think Zig and Odin, have that on the left because that's how it reads. You say an array of int. And, you know, once you stack these more complicated types, you can just read them left to right. But I think it looks weird. I like what they're doing with it, but I think this, I'm so used to it. Like, that just is an int array to me, and also it's more consistent with Java. And I think I've deviated from Java syntax enough that this is its own language, and there's going to be like constructs in this language that Java can't do. So far, at least, I hope, like structs. And ranges, so I think it's fine that we have the same array syntax, which means this isn't right. I can see the benefit of also having stuff on the left, because then you kind of have like a sentinel of like what you're parsing. Tricky. So let's go back to what we had, which was this. So we always expect an identifier. I think then we switch when we have whatever we have next, and we default to just this, and we return that. Cool. So then we say, if we have an open square, we Ooh, I can see another problem coming, but let's just keep going and see where it takes us. So if we get an open square, we need to say token open square, expect open square, and then we immediately expect a closed square because we don't have sized arrays in the JVM. And then we need to yield a new array type expression. With the token open square, close square. That's very cool, but that doesn't handle this, or this, or this, or any depth of array. So we need to like recursively do it, which is why I was like kind of all gung-ho about this, because if it was all before, you can then just call it again and say, oh, I saw another open square. But you can't do that. Yeah. I'm going to leave that as a to-do. Multi-dimensional arrays. And we'll figure out the recursive way we're going to get that later. But for now, let's make, let's see, you are an expression. So you go here. But I think you have a special, yeah, extends type expression. So you need a span, so that'll be a span from the token to, I haven't given it one of these. Cool. Classic getter all args constructor. Bosh. From the token to the closed square, and you need all of that. Okay, cool. That's complaining because, yeah, we don't have very many case labels yet. Yeah, I'll worry about that later. I don't want to sit here thinking about it in silence on camera. So we have an array type expression. Cool. The other thing we need is an array literal expression. So when we're parsing an expression, if I find, there we go. No, not parse primary. We want this one. Oh, wait, no, I'm wrong. We do want parse primary. Because an array literal is a primary expression. So we have all of these, and here we go. So if we have an open square, I think we've already consumed the first one. Yeah, that's kind of annoying, but I think it's useful for these ones that we've already consumed it. So it's a bit of a different pattern. So we already have the open square, which is called token in this. We just want to say while peak does not equal close square, and cursor is less than token size, we want to be parsing expressions, and these are the elements. So we just say elements, add parse expression, and then if peak does not equal close square, then we just expect a comma, and we don't care about saving anywhere because we never use it. Boom, boom, and then we just expect next close square, and we want that one. And then we just yield a new array literal expression from the token, oh, not from, but, you know, with the token, the elements in the close square, because token is the open square. Okay. Makes sense? Good. Let's do this again as fast as we can. Yep. Whoop. Too fast. If I mess up the inputs on my keyboard, it just like deselects the window, which is very annoying. There we go. We want to call this one open square. From there to there. Good, good. Great stuff. So I think we've got everything parsed. So now the type checker is going to be screaming because I've added some new expressions everywhere. So yeah, here we go. We need to add a new type of type. And not even just a simple type. We need a recursive type, which is the array type. Extends Jura, not Jura, but Jura type. And it's going to be similar to type. If you didn't see the last, I can't remember if it was, I think it was the last one or the one before, where I implemented Jura, implemented type. It's a bit of a stupid meme type, but we can just yoink this and we can do this. And this is the element type. And because this is a Jura type, this will actually allow recursion, because this could be another array type, and that could be another array type. And so this is going to be like that, and that is what the string format of this will be, because if Jura type was, say, an int, this would then be like that. If it was another array type, it would recursively do it like that, so that will work fine. So now we can say, if it's an array type expression, we can do a little bit of recursion. So actually, our type checker is way more friendly to this sort of recursion than our parser. Interesting. Maybe it is easier to just put the arrays on the square brackets on the left. It is weird though. It is kind of off-putting when you first see it. Oh, I'll consider it. So if we have an array type expression, we have ooh. This shouldn't be a token. This should be another type expression. And this will be the element type expression. Like so. Okay. And then the parser, go back here. Yeah. And this be a new. So you see, like that should be recursive. I just move on. Don't worry about it. Don't worry about multi-dimensional arrays yet. God damn it. So we just need so Jura type element type equals parse type array type expression get element type expression. So that will recursively figure out what the elements are, even if they're like multi-dimensional arrays, classes, some generic bullshit we have later. Doesn't matter. It will recursively figure it out. And then it will just simply yield. Oh, interesting. Yeah, we should just force this to be exhaustive, like so. Yeah, and now I can do a yield, new array type with the element type, and there we go. We've type checked that. So what else is it complaining about? We don't type check a array literal, like so. So this is kind of interesting. Come on, there we go. Because if it's empty, we're going to have problems. But let's not worry about empty arrays right now. And in fact, let's say if array literal expression get elements is empty, throw new compilation exception, empty array literals are not yet implemented. And you'll see why in a second. So Jura type element type equals null, then for element in array literal get elements. So first of all, let's have a list of typed expression, and I'll call these elements because I haven't used that yet. And I'll just say elements add. Well, let's do typed expression typed element, and then we will type check the element. Why didn't it like, oh, because it's filled it out too much. There we go. We then say if element type equals null, element type equals typed element type. So on the first element, we type check it and we say, okay, we're expecting the rest of the elements to be the same type as this. And we say if element get type, sorry, not that one, but the typed element get type does not equal element type. Kind of redundant on the first loop, but doesn't matter. We will report diagnostic of a type mismatch. We expected the element type. We got typed element type at the element span. And then we just add typed element. Okay, and then we just yield a new typed array literal, don't we? With the type, with just the elements. And so the reason this wouldn't work if we had an empty array is element type would be null. Yeah, and I don't want to add like an any type that we then resolve. I want to deal with that when I have generics, because this will be like a generic array at that point, and then we can erase it when we assign it to something. Or at least I think that's how it would work. Oh, and this should be expression. Maybe it's kind of redundant to have expression on the end of all of these, and that would then shrink the name of the classes. Something to consider. We want a field for that. Then we could just squonk all of that. Add a getter, add a constructor, do all of this nonsense. There we go. And so the type of this, yeah, we would get the first element of this and check it, but I think it's probably more proper later down the line if we just pass in the element type. Because if we can infer it by other means on an empty array or whatever, that is fine. And we just pass in the element type. Bosh. And so, oh no, sorry. This doesn't return the element type. This returns a new array type of element type. And I think I don't want to be constructing a new one every time we call this. So I think I'm going to call this array type. And do that. And then I only construct it once. Probably will save me about 12 nanoseconds in my entire life, but it feels like I should be doing it. And then, even though this class isn't highlighted red, apparently there are still errors. So, type check type expression. Yes. So, we aren't doing this. If it's an array type expression, we need to Jura type element type equals type check expression. Type check type expression of the element type expression. Why doesn't it like that? There's a type expression. Oh, because it returns a type to type expression. Oh. Yeah, I remember what this is for. Okay, so, and then we just yield a new array typed type expression with the element type. Okay, that's weird. That's very weird. I hate this. I hate this, but I understand. This is for when I want to do like, what's the word? Not meta programming. Maybe metaprogramming, but like being able to take a type as an argument to a method, this is what I would need it for. And I think, yeah, I think it's fine. So this is an array typed type expression. Yeah, and that's. Yes. Extends typed type expression. See, I knew this would confuse me. And it takes super of what? Of a Jura type. Okay. So you take the element type. So you just call super. You're probably complaining because you're not final. Of a new array type of the element type type. God. This is going to be useful one day. And I'll be glad I did all the work for it, but right now this is stupid, and that needs a semicolon. Okay, and then, okay, we get rid of these breakpoints. Type checker is happy. Molto bene. I think the lowerer should be happy because I didn't add any new statements. Yeah. The bytecode emitter, however, is going to be annoyed. Because... Ooh, here we go. This should be very interesting. So, if it's an array type, the way that you do a type descriptor with an array is you just have a left open square and then the type. So this is really easy. It's just, in fact, I could probably do it like this. It's just that plus the type description of its element. And let's put that at the top because it's slightly longer. Okay, one compilation error down. Yeah. Oh, this would be nice if I could actually merge these, but I can't, even though I don't use the object. I think it's a return. Let me double check. Java bytecode instructions. So it's a return. Return a reference. I think that is what you use for an array. Because there's... what other? Because yeah, there wouldn't be a return. There's other like AA, yeah, like AA load, which is loading a reference from an array. Because A load is loading, yeah, here, loading a reference from a variable, and then you prefix it with A for it to be an array. Yeah, I was just like, there isn't an AA return, but that would be something completely different, and that doesn't make any sense. Oh boy. And then printing an array. Huh. Yeah. But also, I think I can simplify this by just using the descriptor code. Let's not worry about that now. So if we're printing an array type, maybe we... What happens if you print an array in Java? Let's find out. If I... well, I'm going to need to solve all these compilation problems. But if I go to Jura.java and I do something like int foo equals 0, 1, 2, 3, 4. Sure, that works. And then I sout it to that. Implicit call to toString. Yeah, so it's going to toString it. So which makes me think there isn't actually a overload for printing an array or print learning an array, because yeah, it's taking an object. Yeah, it calls the first string value of to get the string value and then behaves as though it provoked. So I think that's just going to print something incomprehensible. So I'm just going to say that it is not implemented. Printing arrays is not yet implemented. And then, yes, so if we're loading a variable of type array, we get to say a load, I believe. Let's see. So a load is a reference. Yeah, an AA load, yeah, we already looked this up, is loading a reference from an array. So yeah, arrays are reference. Okay, cool. And so then, surely there should be somewhere else it's complaining then. Because if that's when we load the variable, what about when we store the variable? So here's statements, conditional, load, return. Assignment. That's what we... No, that isn't what we fixed. Okay. So if it's a variable, here we go. We hard-coded it to an iStore. So that's why it didn't complain. So we need to switch on variable expression get variable, which means we should probably yoink that out to a variable. Switch on the variable type. And now we have all of these. So for int and for bool, we do that. For error, we throw a new compilation exception because this should be unreachable. Type. Yeah, we shouldn't be here. And then here I will say variables of type are not yet implemented, which I think is the same as the other one. And then arrays are just going to be move visit var instruction a store to the index. And then we return. Yeah. Oh yeah, this was when I was trying to figure out the binary chains of like assigning to an assignment, and I couldn't be bothered to figure it out. So let's just do this song and dance. There we go. Okay, I was like, surely something else should have lit up then. Okay, so we can store arrays, we can load arrays, but can we emit arrays? Not yet. So let's just clean that up a little bit. So let's go back to the list bytecode. So I did see a new array. Well, that's the one that's full of references, but there was a new array opcode somewhere. I think I just went straight past it. New array. So this takes a type of a reference. Oh, sorry, a primitive type identified by a type, and it takes a count, and it returns the reference to that array. So it doesn't take the elements. Okay, so we're going to have to create the array with the count of elements, and then we're going to have to manually set the elements, I think. So let's do that. So we need to get elements size. So this will be count. No, let's call it size for consistency. And then we want to move visit. Is there array? Multi-A new array instruction. No. What kind of... Is it a type instruction? This is annoying. Like, OW2ASM has all these different functions for different, like, opcodes, but there's no, like, compile time checking for which opcodes go with which functions, because they're all just ints. So you don't find out until you possibly run the emitted Java bytecode that you picked the wrong one. So it's not a type annotation. What would it be? It's not int. It's not a type Could it be a type instruction? Field, local variable. Interesting. Don't know what that one's for. That sounds like something we should probably learn about. Ooh, line number. Oh, that's probably useful for like reporting like proper exceptions. I don't know why I've never looked through this properly. Yeah, I don't know which one it's supposed to be. It's not a field. It's probably a type instruction. Let's try that one. So So the opcode is going to be new array. The type is going to be based on the element type. Get type. And this is going to be... can I say that this is an array type? Yeah, it doesn't let me do that. Oh, hang on. Oh, and then it's happy about me overriding it like that. Ooh, okay. And then this should be fine because I construct it with that. So I can say switch on this element type. Ha ha ha. Okay. If it is an int, then we say I. And I'm going to leave the others blank for now to see if that's correct. So I think I can probably run that now, and I don't think I've actually told it to compile arrays. No, it's still compiling Fibonacci. Array Jura. Type mismatch, expected int, but got int. Aha. Here's a problem. I'm using the primitive equals, I think. I knew this would bite me. Yeah, look at this. I keep using the primitive equals to compare types, but now that doesn't work because I have complex types. When I had the singletons of like ints and units and bools, it was fine. But now it's not. So I think I need a... actually, I think I need to just... override equals in these ones. Public boolean equals, and just say if element type equals, oh, and this needs to be array type other, or Jura type other. Why isn't it not like that? Oh, it has to be object other, doesn't it? Yeah. If other instance of array type, else return false. If the element type equals and we other array, so I can say get element type, and then I can just return that. Okay, that's that. And I should probably do the same for type. And do is other type, and then it's if the Jura type equals the others, get Jura type. Okay, that's half of it. And then the type checker. So every time I do this, I should say if not this equals that. I don't think I need that bracket. Cool. Let's search for every other place we throw a type mismatch. Yep. So if condition type does not equal that, so we if I say if bool type instance equals this, but not. Cool. Next. That's the same condition because it's for while instead. Yep. Type is not equal conditions. Is that? Yes. Can this be null? We always have an initializer. And we always have this. Okay, that's fine. If equals. If not equals. And then this one. So if that equals this, but not. Okay. Ooh. So it's not visit type instruction. Is it just visit Which one of these fucking things would it be? Definitely not that one. Not switch. Not a parameter. Try catch. No. Type annotation. No. I thought it'd be a type instruction. Let me go do some Googling and then I'll see. Okay, I found this method visitor. So I think method visitor has all of the Java doc. So opcode should be new array and then the operand. Okay, so they provide opcodes. What was it? Opcodes, a t_int. Okay, that makes sense. Still doesn't like that. One argument but found. Oh, visit int instruction. There we go. So that means I can do this because there is a t boolean. Interestingly enough, maybe the JVM does some optimization under the hood where it like packs the booleans, and that's why there is a different boolean type here, but there isn't when it's just a standalone. That's pretty interesting. If it is an array type, we throw new compilation exception. Multi-dimensional arrays are not yet implemented. Error type should be unreachable, so throw new compilation exception unreachable. Type, yeah, I mean unit type should be unreachable. Let's move those to the top. Type is going to be like a reference, I think. So I think I'm also just going to throw a compilation exception and just say arrays of types are not yet implemented. And I forgot a semicolon over here. Okay, and then these are all ignored. Classic. Yep. Bosh. So I need to omit the size on the stack first, because new array, if we go back here, it consumes a count. So yeah, this is what the parameter, this is the opcode, this is what's on the stack, and then this is what it leaves on the stack. Okay, so we need to visit int instruction, and it's going to be a sipush, because assigned integer push size. Let's try that. Okay, no compilation errors, no anything, and it pushes a new integer of 5 elements, which is how many we declared. So now we just need to go through all the elements, emit them, and set the element. How do we do that? Probably a store, if I was to guess. No. Because A's are always references. So how do I store a reference in an array? Yes. How do I store a primitive in an array? Ah, here we go. Load a byte or boolean from an array. So there's probably a BA store. Yep. A byte or a boolean into that. So like we have bypush and sipush, we're going to have bastore and sapstore. Cool. So go back to the bytecode emitter, and so we say for bar element in whoops, not like that. Array literal elements. Emit in this method visitor the element. Excuse you, sir. The element, and then we need to switch on the element's type. And then we need to do all this crap again. So, first of all, those. Then array type, multi-dimensional arrays are not yet implemented. And then type, yep, there we go. So put those up the top. Actually, no, don't need that. Oops. There we go. So, if it's a bool type or an int type, it's the same instruction, but we can't collapse them because it's very annoying. It is a si push. Not an si push, an sa store. And it's just a regular old instruction. To be fair, this could just be a BA store. So later on we can have shorts and bytes sized. Sorry, not shorts and bytes, but like bytes and integer sized types. But currently every integer is an integer width. There are no bytes. Once we get into like characters and things like that, we can add the bytes, but not right now. I think that's it. Yeah. Let's have a look at what we emitted. Nonsense. That's what we emitted. Cool. BA store. Aha, yes. It takes the reference to the array, the index, and then the value. Okay. So, how do we do that? So let's have a look at what we have on the stack. We push the count. We then consume it and push the reference to the array. So currently we have array ref. Okay. We need to then push the index and the value. So we just need to, for each one, so let's replace this with an indexed for loop. There was no need to do that, but sure. We emit the element. So first of all, we need to emit the index. Cool. So we have here array ref. Here we have array ref index, and here we have array ref index element, or value, which is exactly what it wants. And this consumes all three and returns nothing. So at the end of this loop, once we do the store, we have nothing on the stack, which means when we come round again, we're going to have nothing. We're going to push the index and the element, and this isn't going to work because we don't have the array ref anymore. So actually, the first thing we want to do is visit a dupe instruction. So what that does is we start off with the array ref, we dupe it, so we have array ref, and then we have that, an index, then we have that, index, and value. This then consumes these three, leaving us with the array ref on the stack. So when we come back around to the next loop, we have the array ref. That does mean when we finish, we have the array ref still on the stack, and that's not allowed because... Is that not allowed? No, that is allowed. That's what we want. This is an expression. It's supposed to return something. So this just returns the array ref, which is perfect because we'll be returning this. Sorry, we'll be assigning this to the variable, so we want the reference to it, or we'll be passing it in as a like a function parameter, so we want the ref. So that's fine. We want to leave it on the stack. So now if we look at what we emitted, there we go. Okay, I did fix this. I thought I still had like 0, 2, 3, 4, 5, and I was like, oh, did I just store the index? But no, I think if I do like 5, 3, 1, that should be fine. Yeah, there we go. Array literals. we can now do that. And then I could probably have like something like function foo, which takes in an array. Yeah. And then does nothing with it because we can't do anything with arrays yet. And then can I say foo x? Does that compile? No, of course not. Emitting type is not yet implemented. Well, why did you emit a type? With array type, get element type. When did I construct you? Jura type, element type. Interesting. What do I get here? Int. Well, hang on. That's not all of them. Okay. So, where did it complain? What was I doing when it complained? You were emitting a function param. Yes. So, let's have a look at what we got here. So param type function parameter. Yeah, it thinks it's a type. Interesting. So if we go to the type checker for type check function parameter in here. So the identifier. Ooh. Yes, that's the variable name, and then we want to type check the type expression in the function parameter, which is an array type expression. Yeah. Which has basic type expression of int and open square, close square. So we come into here. So we have array type expression, which has a basic type expression of int here. So we should come in again, come in here, parse the type, which is an int, return a basic typed type expression, which comes out to an array typed type expression. So the typed expression is now a type of int. Oh, hold on. That's not right. Super new array type expression. I think I called this somewhere I should have called I should have called get Jura type. So if I go back to here, build type variable, no. Hang on. Get element type, get variable type. So variable has a Jura type. So when I create this, I am using the Jura type. Wait, I was already here, so if I step through all of this, yep. So my typed expression has a Jura type of array type. Okay. And the element type is an int. The element type is a type. And why is that? Pray tell. Like that? No. No. New array type, element type, get Jura type. There we go. Good God. Okay, I knew that was going to bite me in the ass one day. There we go. What was I even doing? What was the last thing I did? I did this. And that compiled, right? Yeah. So I'm allowed to do that. What does that compile to? Yeah. So I can pass these into functions. God damn. Okay. Oh. I think I want to take a break. But let's set up what we're going to compile after the break. So I want to say while, let's say I equals 0. I really need to get for loops into this program, into this programming language, but maybe not yet. Or maybe it's a good idea to add that with arrays. We'll see how we go. So while I is less than x dot length, that's going to be kind of a spicy one. Let's add that afterwards. Let's say 3. Print x I. So they were going to do array indexing next. And hopefully that's not going to be too much trouble. And then afterwards we can maybe do some reassignment. So we'll try that. And then maybe we can do like x.length, because that had its own here has its own bytecode instruction, so that should be pretty easy to add. It's just the parsing of like accessing methods or accessing fields. We don't technically have that yet, so I might leave that until we do. But we'll see. I'm going to take a bit of a break. Maybe I'll come back another day, because I've been going for quite a while today. And then we'll implement this. So I'll see you then. Okay, so let's add array indexing. So I was thinking of adding it to this method. So we've parsed an expression, and we kind of want to then look ahead to see, oh, is it going to be an index? But we kind of want to do that forever, because if we look at this, like, we can index this once, and this is a you know, a variable expression, but this could be anything, right? This could be a method call which returns an array that we immediately index. It could be like an accessor onto a field of some object. So we need to have parsed some complete expression, and then we need to then look ahead to see, is there an open square? I think. I know you could probably give the open square token some precedence, and then this might get parsed as a binary expression. But it kind of doesn't fit the pattern, because then you have this other token at the end you then have to parse. So you kind of have to handle this specially. At least I think. Maybe there's a better way to do this. But I can't think of one. So after we've gotten a primary expression, in fact, we could probably just add it to this. Yeah. So I could just say expression equals this. Oh, it doesn't like that. I'll call this primary. And then I can just say while cursor less than excuse me. Is it called program? Oh, sorry, we're in the parser. Less than token size, and we can just say switch on peak, default, return primary. And then we can have we can just default break. So if we see an open square, we want to expect the open square. We want the index as an expression, and then we want the closed square. Like that. And then we just need to say that the primary is now a new array index expression with the primary as the index E, with an open square, an index, and a closed square. So now we do this again. Cool. This is just going to be expression. Bind them to fields. Get rid of the constructor. Add our good friend Lombok. Oh, my keyboard is in US, or in UK. It needs to be in US. And then we need to do all this. And the span goes from the expression to the final closed square. There we go. Yeah, I guess that is unnecessary. And then this will this will keep going. Hang on. This will keep going until we run out of tokens. This is gonna go forever. Yeah, I don't like that. So we do need a default that breaks. Is this? Yeah, this is binding to the switch. Okay, so it does need to be like that. Okay. Yeah, we'll leave it as a switch because we might add more later. Okay, that's fine. So then we're going to keep assigning to primary this, and we could do something similar for like method accessing with dots, but I think that kind of works as a binary expression. Yeah, because like you would have to have this be its own expression, and that's kind of weird. So I'm going to leave it. So our type checker is now going to complain because we have a brand new kind of expression. And thankfully, we should have all of the tools needed to be able to do this. Excuse me. There we go. Sorry, that's what I meant. Sorry, it's very early in the morning when I'm doing this. I just woke up and I was like, I could see how I was going to implement this, and I was like, I've got to do this. Which is probably why my voice sounds a bit more gravelly than it did in the previous section. Okay, so, first of all, we want to type check the expression. It doesn't like that. Let's call this the index E. Indexed? Indexed. And this has to be indexable. So currently the only indexable type we have is an array. Maybe when we have lists, maybe we're allowed to index lists with the same syntax. Take that, Java. So we need to say if indexed get type instance of array type, and it needs to be not one of those. We would say report diagnostic. What does Java do? If I say int 10, int x, sorry, sure, C, and I try and do this, array type expected found int. That's pretty good. Array type expected, and we actually got index type at array index expression span. Let's add that one. This is the actual, and that's the span. Diagnostic array type expected got blah at the span. I need to format it with the actual. Cool. So now we need to, this is the actual index, we need to type check the index. And didn't I, yes, so I need to say if index get type equals int type instance. So if it doesn't equal that, it's a diagnostic type mismatch. So we expected int type, we got that, and we got it at the array index, get index, span. Cool. So we have an array, and it's being indexed by an int. So we can now just say yield a new typed array index expression, which has the index and the index. Yeah. I'll just call that expression. Cool. Bind to fields. Cool. And then, so the interesting thing about getting the type here is we have to do return expression get type, cast that to an array type, which we're allowed to do, and then get the element type, because we're indexing it, so we're going to be returning an element of the array. Maybe we could have instantiated it with this element type, so we don't have to constantly cast and access it when we call get type, but I don't think it's going to matter. So that works. Our lowerer doesn't lower expressions. So now, ooh, and something else we need to figure out. We'll do it later. I was going to say we need to make array index expressions L values, because they can be on the left side of an assignment. But we'll get to that. Oops. What did I just do? There we go. We'll get to that when we get to that. So, array index. Let's just call that array index. So I'm pretty sure we have, these BA SA store instructions. There's going to be a load variant, and it's going to be way easier to set up than this. So we need to emit the expression to get the array ref onto the stack, and then we need to emit the index. So you have now the index on the stack, and then I think we just need to switch on the expected type that we're going to get. I'm just going to yoink all these because this has everything I want. So instead of BA store, it's going to be BA load, and instead of SA store, it's going to be SA load. And I think that's it. This is going to take ages because it's my first time this morning running it. So the thing I'm going to be interested in seeing is, okay, yeah, it's going to be fine. It's going to be fine. Might be a bit wonky, but I think it has to be a bit wonky to do assigning to arrays. That compiled with no diagnostics. So if we run it, it explodes. Okay, why did it explode? type array of integer is not assignable to array of s. Okay, I think Java has just pranked me. There is an IA load to load an int from an array, and I think maybe that's what it's complaining about. So this isn't signed like the other s's. So like sci-push is a like signed integer push. This is an integer array store, and then we need an integer array load. I think it's very annoying that it pranks you like that. Bad type and operand stack. List of I is not assignable to integer. Why is there a list on the stack? Or an array of integer on the stack? Let me simplify this greatly. So let's see if the error is in our array indexing code. Okay, yeah. So it doesn't like that, but now we have a much simpler example, which is nice. So we're failing at I store 0. So what is I store 0? Because that doesn't sound right. I'm going the wrong way for I. I was already on I. IA store. Yeah, storing an int value into variable 0. Are we failing here? Yeah. Okay, we've managed to break the array assignment code. I store 0. How? So when do we do I store? We do it here. Okay. But we never hit that instruction. Oh, we have one here. Okay, because we didn't put the switch here. Okay, pass me as my enemy. So we have to switch on the variable type, and I'm just going to yoink this one because it has all of the stuff I want. So if it's an array type, we want it to be a visit instruction. How do I load an array type? Is it just a load? Because it's a reference? Yeah, it's just a load. And then we have, and then this will be what do you have before? Oh wait, hang on. No, it's just storing the index. Okay. So this is going to be a store. This would be, is it bi store? B store? Just I store? Sure. Try that again. Still doesn't like it. A store. Local table overflow. Because these are var instructions and I need to pass them the index. Okay, it's all coming back to me now. I wish I'd done this with a switch before and didn't just hard code it to an int, but here we are. Oh, it just worked. Okay, so if I printed the first one and then the second one, does that feel really slow to you? No, okay, it was just the terminal being weird. Cool. So let's go back to the while loop variant. We might also want to increment I. I really need to get for loops in this language just so it's easier to do shit like this. Beautiful. What happens if we overflow? Okay. I like that. That works. And we could do like static checking if we wanted to, if we could figure out the value of the index at compile time. In fact, I'm going to put a note to do that. To do compile time evaluation of index to check for out of bounds. Cool. So we have this. Let's now say x0 is now 7. And then we print x0. So I think it's going to complain with an error saying that the array index is not an L value. Variable expected. Okay. We can deal with that. So if I go to diagnostic and search for variable expected, that's literally what it's called. Okay, that's a bit of an odd. I'm gonna change this because it's not really a variable now on the left. Let's just say expression is not assignable, and I'll just say expression is not assignable. Yeah, I think that's better. So how do we fix that? Well, that complains because the binary expression left-hand side is not an L value. By default, all expressions are not L values, and it's only the binary expression that overwrites it if the right-hand side is an L value, or the variable expression is an L value. So I think we just need to say that array index expressions are L values. And then I believe the bytecode emitter should throw an exception. Yes. It should say an unhandled L value. Boom. An assignment typed array index expression. So all we need to do is just say if the LHS is an instance of a typed array index expression, and I'll just call this an index expression, then we just need to, we've already, have we already omitted the LHS? No. We haven't omitted anything. So if we omit the RHS, so we have our assignment, we just need to omit the LHS actually. So on here, on the stack, we have the array ref and then the value. And then I think it's just the same thing we do when we initialize this. We just switch on the type, and then we call BA store or IA store. And this will be on the RHS type. And then we return. No, not quite. So we have the array and the value, but we don't have the actual index. So we need to actually omit the index as well. So we do that after the expression. Okay, so we just need to omit the index expression index. I think so. So we don't want to omit the LHS quite like that. We want to do that. I think that's what we want to do. Okay, no compilation errors. Okay, interesting. What went wrong? Because I got rid of the bloody... Okay, we're adding for loops after this. So that I don't have to deal with this anymore. Array out of bounds. Because I left that in. Okay. Glad that this language is keeping me honest. Ooh, index 7 out of bounds. Okay, we've messed up the order. Let's make some room. So we emit the expression, we emit the RHS, and we emit the index. The index should come first. There we go. Cool. So now instead I could do xi equals I. And then do this, and yeah, cool. I could even... No, hang on. I could. So I want to just test to see. You know, let's not do it in there. I want to test to see if you can do like a binary expression in here. I don't know why I'm doing it like this, but yeah, whatever. I just want to check that you can have arbitrary expressions inside, and you can. Okay. I think that's kind of arrays done, and I think I'm going to leave it there. This has been an enormous part. I thought I was going to do this really quickly, but I don't think I did. So I'm going to leave it there, and I think next time we're going to start doing some like sugar around like for loops and like for in loops and stuff like that. And that should just make the language a bit more usable. Like, that was kind of annoying having to do this. I think it might also be nice to add more sugar like this and this, perhaps, just to make my life a bit easier. And none of that should involve any bytecode changes, except for maybe ink. There might be an ink instruction. iInc, yeah, and there's probably an iDec. Is there? Oh, there's no deck. Interesting. Okay, so you can increment in the bytecode, but you can't decrement in the bytecode, if I'm reading that right. Oh well. So yeah, next time we'll tackle that, and then I think the next thing after that will be types, classes, maybe structs if I can figure out how I'm going to do structs. Yeah. Okay. Thank you very much for watching. If you made it this far, please leave a comment, leave a like. Let me know what you're enjoying about this series to have made it so far. And I'll hopefully see you in the next one. Bye-bye.